Imagine waking up at 3 a.m. to an alert that your production API budget for the entire month was incinerated in just 4 hours. This isn't a hypothetical scenario, it's the reality of recursive failure in autonomous agents. In the field, we often see agents enter what I call the infinite reflection loop. The agent tries to solve a task, encounters a minor syntax error, attempts to self-correct, but uses the same flawed logic that caused the error in the first place. Because the prompt instructions lacked a terminal exit condition, the agent keeps calling the LLM, burning tokens, and hallucinating progress. By the time the monitoring system catches it, you've hit your rate limits and your system is paralyzed. This is the silent death where the agent isn't crashed, but it's effectively dead because it's stuck in a loop of unproductive reasoning. This happens because most developers treat agents like chatbots, not like state machines. By the end of this lecture, you'll know exactly how to build the circuit breaker and the state management logic that stops this madness before it drains your bank account. To survive in 2026, your agent architecture needs to be more than just a loop. It needs to be a resilient orchestration. A robust system doesn't just tree again. It utilizes an external observer node that monitors the semantic distance between consecutive thoughts. If the agent's reasoning hasn't evolved for 3 iterations, the system must trigger an automated escalation or a reset of the context window. Real-world resilience means building a multi-layered defense where the agent is forced to justify its next move against a set of constraints, or if a next API call is even allowed. We move from "I hope the prompt works" to "the system ensures the loop terminates." This requires a fundamental shift in how we think about agentic workflows, treating every turn as a state transition that must be validated by a separate logic gate. But how do we transition from a lucky prompt to a guaranteed, engineered system? Let's talk about the engineering shift required to bridge this gap. The biggest mistake I see senior developers making today is staying stuck in the prompt engineering mindset. In 2026, prompt engineering is just a small subset of what we actually do, which is loop engineering. Simple single-turn prompts are for toys. Production agents require complex orchestration. We are building systems where the prompt is just the configuration for a much larger engine that manages memory, tools, and cross-model verification. Think of it as moving from writing a script to designing a microservice. You need to define clear input-output schemas for every step of the agent's internal thought process. When an agent decides to use a tool, that decision must be intercepted, parsed, and validated against a schema before execution. This system thinking approach ensures that even if the LLM hallucinates a tool argument, the orchestration layer catches it before it hits your database. Is there a standard for these gates? In 2026, we have a specific stack that defines how these reliable systems are built. In the 2026 landscape, the Agentic protocol stack has become the standard for high-reliability systems. We no longer just send strings to an API. We use protocols like MCP Model Context Protocol to standardize how agents interact with their environment and other agents. The stack starts with the foundation model at the bottom, but the real work happens in the layers above. The context mesh for shared memory, the tool orchestrator for safe execution, and the reliability layer for error recovery. This architectural shift is what separates a demo from a production-ready agent that can run for weeks without human intervention. Mastering this stack is no longer optional for back-end engineers. It's the core of how we build intelligent software. We have seen the what and the why of agent failure, but now we need to get our hands dirty. In the next chapter, we are diving deep into deconstructing the specific failure modes that kill your production agents and how to diagnose them before they occur. In the field, we don't just see bugs, we see agentic collapses. The most common is the tool use hallucination. You've likely seen an agent attempt to call a function like get user financial report. That doesn't even exist in your schema, simply because the model felt it should exist. When the system returns a 404 or an undefined error, the agent doesn't realize its mistake. Instead, it enters a semantic loop where it rephrases the exact same hallucinated tool call repeatedly until the max iterations hit or your token budget is drained. This isn't a coding error in your Python script. It's a failure of the agent's internal logic to reconcile the external environment's reality with its own internal probability map. We categorize these into 2 main buckets: tool use errors and logic deadlocks. If you don't build a circuit breaker for these hallucinated calls, your agent becomes an expensive loop of nothingness. But wait until you see how these simple errors transform into a destructive spiral. Even your best retree logic can't stop. There is a massive difference between a healthy iterative loop and a destructive infinite loop. A healthy loop shows progress. The agent tries a search, gets a result, refines its query, and moves closer to the goal. It's moving down a gradient. A destructive loop, however, is stationary. It's an echo chamber where the agent's own previous failed reasoning is fed back into the next prompt as context, reinforcing the mistake. I've seen agents spend, 50 in 5 minutes because they kept apologizing for an error and then immediately making the same error again in the very next turn. This self-correction paradox occurs when the feedback loop isn't grounded in external validation but only in internal LLM logic. To fix this, your architecture must detect 0 progress states. If the state delta between iteration n and n+1 is 0, you must break the loop. You might think adding more detailed prompts is the solution, but as I'll show you next, prompt ambiguity is actually a hidden catalyst for non-deterministic crashes. Why do these loops happen? It usually traces back to root cause analysis of your prompt design. Prompt ambiguity is the silent killer of deterministic execution. When you give an instruction like process this data efficiently, the agent has to define efficiently on the fly. In a multi-step loop, the agent's definition of efficiently might drift. By step 5, it might decide that skipping validation is efficient. This leads to non-deterministic execution failures where the agent works perfectly 80% of the time but fails spectacularly the other 20% due to branching logic it invented for itself. We call this probability map collapse. The agent's path branches so many times based on ambiguous instructions that it eventually hits a state where no valid action exists. Mapping these failure paths is the first step to building a resilient agent. Now that we've mapped the logic failures, we need to talk about the memory leak of the agent world, how state management literally rots the agent's brain over time. Context window management isn't just about fitting more tokens, it's about managing state drift. Think of an agent's context as its short-term memory. As the loop progresses, the window fills up with tool outputs, error logs, and intermediate reasoning. This creates a massive signal-to-noise problem. The original system instruction, the agent's core objective, gets pushed further and further back in the context, losing its attention weight. Eventually, the agent starts prioritizing the last 3 error messages it received over the actual goal it was supposed to achieve. This is where agents lose their mind and start behaving erratically. In a 2026 production environment, simply dumping everything into the context is a rookie mistake. You need to actively prune and summarize the state to keep the objective signal high. If the agent is going to lose its mind every 10 steps, you need a way to save the game, and standard database writes are not enough. In long-running agent tasks, checkpointing is your only safety net. You cannot treat an agent run as a single atomic transaction. If an agent is performing a 50-step data migration and crashes at step 48, restarting from 0 is a disaster. We need granular state persistence. This means snapshotting not just the final output, but the entire reasoning graph and the memory state at every critical decision point. In modern orchestration, we use a state machine approach where each transition is committed to a persistent store. If the LM provider goes down or a tool timeouts, you can reinstantiate the agent from the exact node where it failed. This checkpointing allows for human-in-the-loop intervention. A developer can fix a state variable and tell the agent to resume from node 48. Even with perfect checkpoints, there's a silent killer in the network: the time it takes for a tool to actually finish what it started. One of the most frustrating failures I see in production is observation lag. Imagine an agent triggers a cloud resource deployment via an API. The agent then immediately checks if the resource is active. Because the cloud provider takes 30 seconds to provision, the API returns pending. The agent, lacking a concept of temporal delay, interprets pending as a failure to reach the desired state. It then tries to trigger the deployment again, or worse, tries to fix it by deleting and restarting. This creates a race condition between the agent's fast loop and the external world's slow reality. In 2026, your agent logic must incorporate asynchronous awareness. You need to design your prompts to understand that not finished is not the same as failed. Identifying these failure modes is the diagnostic phase, but how do we build the control system to prevent them? In the next chapter, we're going to architect the loop control system from the ground up. In the real world, a single agent loop is a recipe for disaster. If you let the same LLM generate code and then ask it, is this code correct? It will almost always say yes because of self-bias and hallucination. This is where the judgment gate pattern comes in. We introduce a secondary verifier agent, often using a more reasoning-heavy model like GPT-4 or a fine-tuned Llama 370B, specifically to tear apart the primary agent's output. The verifier doesn't build, it only critiques. It looks for logical fallacies, security vulnerabilities, or simple compliance with the user's original intent. This separation of concerns creates a double-check mechanism that is the first line of defense in production systems. Without this gate, your agent is just a runaway train of optimistic hallucinations. However, even the best verifier can't catch everything if the output format itself is messy. Do you think a simple yes or no from a verifier is enough for a robust system? If you are still parsing agent outputs with rejects in 2026, you are building on sand. We need hard constraints using pedantic or structured output schemas to ensure the agent's thoughts align with our system's requirements. By defining a strict schema, we force the LLM to follow a specific type-safe structure. If the model fails to adhere to the schema, the system catches it at the validation layer before it ever touches your database or API. Using pedantic v2 or similar libraries allows us to define not just types, but also ranges, rejects patterns, and custom validators. This turns a fuzzy LLM output into a reliable data object. But here is the hard truth: models will still fail to follow these schemas about 5% of the time on complex tasks. When that happens, simply throwing an error is the worst thing you can do. So what do we do when the schema validation fails? When a tool call fails or a schema is violated, beginners often just restart the loop or give up. Experts use corrective prompting with exponential backoffs. Instead of a generic try again, you must feed the exact error message, whether it's a Python traceback or a pedantic validation error, back into the agent's context. You tell the agent, your last output failed for this specific reason. Fix it. We also implement backoff strategies because hitting the same rate-limited API or a struggling model context repeatedly won't solve the issue. However, you cannot loop forever. You must set a max retrieve limit, typically 3 or 5, to prevent infinite billing loops where an agent keeps hallucinating the same mistake at your expense. But what if the agent is stuck in a logic loop that the code can't detect? That's when we need a break-glass procedure involving the most reliable computer ever made, a human. Human in the loop, or HTL, isn't just about clicking approve. It's about defining the escalation threshold. In high-stakes environments like financial transactions or production deployments, you design the agent to pause when it hits a high-risk tool or when its verifier score is below a certain confidence level, say 0.7. The system state is saved and a notification is sent to a human operator. The operator can then inspect the agent's reasoning trace and provide a nudge or a direct correction. This turns the agent from a risky autonomous bot into a powerful co-pilot. If your architecture doesn't have a way to pause and resume the state, you're not ready for production. But how do we manage these complex states and pauses without the system becoming a tangled mess of spaghetti code? Let's look at the frameworks designed to handle this orchestration. Choosing between orchestration frameworks like LangGraph, Temporal, or even custom state machines is a critical architectural decision. LangGraph is excellent for defining agents as cyclic graphs, allowing you to explicitly model loops and conditional edges. However, if your agent needs to run for days waiting for a human or a slow external process, you need a workflow engine like Temporal. Temporal provides durable execution, meaning if your server crashes in the middle of a complex agent loop, it resumes exactly where it left off. In 2026, the trend is moving toward stateful agents, where the memory isn't just a list of strings, but a managed database state. Picking the wrong tool here means you'll be fighting the framework instead of building the agent. But why can't we just use a simple linear DAG for agents? The answer lies in the fundamental nature of reasoning. Standard software engineering loves directed acyclic graphs, DAGs, because they are predictable. You go from A to B to C and you're done. Agents, however, require cyclic graphs. An agent might go from research to code, realize the code fails, and go back to research. This cycle is what gives the agent its power, but it's also why agents fail so spectacularly. Without guards or checkpoints, a cyclic graph becomes an infinite loop that drains your wallet and never terminates. Every cycle must consume energy, meaning you track the number of iterations and the total tokens used. If you exceed a budget, the graph must force an exit. This transition from linear to cyclic thinking is the biggest hurdle for traditional developers. But what happens when the graph gets so big it becomes unmanageable? You split it up. In large-scale systems, we move away from one giant God agent and toward distributed agents. We use a supervisor pattern where a top-level agent breaks down a task and delegates it to specialized sub-agents, one for SQL, one for web search, and one for data visualization. This reduces the context window noise for each sub-agent, making them more accurate. However, this introduces communication overhead. You have to manage handoffs where agent passes its state to agent B. If the handoff is poorly defined, the context is lost, and the second agent starts hallucinating. Managing this distributed state is essentially a microservices problem, but for LLMs, it sounds complex, and it is, but it's the only way to scale. But wait, if we have all these specialized agents, do they really have to wait for each other one by one? Latency is the silent killer of agentic UX. If an agent takes 2 minutes to think, because it's running every tool sequentially, your users will leave. Parallel execution is key. In modern orchestration, we identify independent nodes that can run at the same time, like searching multiple sources or running tests on different code modules simultaneously. We use fan-out to trigger these actions and fan-in to aggregate the results. This doesn't just save time, it also provides the LLM with a richer set of data points to reason from in the next step. However, aggregating conflicting data from parallel paths requires even smarter judgment gates. We've covered the blueprint of the system, but the real test is when it hits the messy reality of production. In the next chapter, we're going into the trenches with real-world war stories, crashing agents, infinite loops, and the radical solutions that fix them. In production, the most innocent setups are often the most dangerous. Imagine a multi-agent system where a writer agent and a researcher agent share a local SQLite database for state management. Everything works fine in dev, but in a high-concurrency production loop, they start hitting databases locked errors simultaneously. Agent A tries to write a summary while Agent B is mid-transaction reading the context. Because the LM doesn't understand pragma busy timeout, it sees the error, thinks it's a transient failure, and retries instantly hundreds of times per second. This isn't just a lock, it's a recursive conflict that eats your CPU and your API budget. Theory says SQLite is ASI compliant, but in the world of autonomous loops, standard locking mechanisms become a recipe for infinite retries. This is where your smart agent becomes a very expensive, very dumb hammer. But wait, why didn't a simple tray catch block save us here? The answer lies in how the agents interpret the failure itself. To solve this, we had to move beyond simple database settings and implement a master orchestrator or a traffic controller for the agents. We didn't just give them access to the DB, we gave them a serialized request queue. When an agent wants to update the state, it emits a state change request rather than executing SQL directly. The orchestrator validates the request, checks for existing locks, and applies an exponential backoff that the agent is forced to respect. We also implemented a preemptible lock system where the orchestrator can kill a low-priority summarization agent if a high-priority emergency response agent needs the write-ahead log. This transition from direct access to mediated access is what separates a prototype from a 2026 grade production system. You must treat your agents like unruly threads in a multi-threaded OS, not like independent users. However, even with a perfect orchestrator, another demon was lurking: starvation. Does this solve the problem for good? Not quite. Let's see what happens when the orchestrator itself becomes the bottleneck. The biggest takeaway from the SQLite disaster wasn't about the database. It was about shared memory architecture. Experienced engineers know that if two agents are reading and writing to the same context, they will eventually hallucinate over each other's updates. We learned to implement namespace isolation. Each agent gets its own workspace, and shared data is only synchronized to specific sync checkpoints governed by the orchestrator. This prevents logic drift, where an agent changes a variable that another agent was using for its current reasoning step. Always remember, in 2026, agents are fast, but their memory consistency is fragile. You need a checklist to ensure your memory architecture doesn't become a liability. We've compiled the critical must-haves for multi-agent safety that we use in every project. But even if your memory is safe, how do you know when an agent is going rogue in real time? That's where observability comes in. In the world of agent loops, standard logging is useless. If you're just looking at std, you're blind. You need full traceability. This means tracking every thought, every tool call, and every hallucination back to a specific prompt version. Tools like Langsmith or custom OTLP traces are non-negotiable in 2026. Why? Because of logic drift. An agent might successfully complete a task, but its reasoning might be slowly diverging from your safety constraints. For example, a customer service agent might start giving unauthorized discounts because it found a logic loophole in the prompt chain. You need to catch this before it escalates to a full-blown financial loss. We set up real-time semantic alerts that flag when an agent's internal reasoning contains keywords that shouldn't be there. Monitoring isn't just about is the server up. It's about is the agent's logic still sane, but checking logic alone won't stop a runaway cost spiral. Speaking of costs, one of our biggest war stories involved an agent getting stuck in a tool calling loop that cost $800 in a single lunch break. The agent was trying to format a file, the tool failed, and it retried with a slightly different prompt again and again. In 2026, you must define budget thresholds and automatic kill switches for every single agent run. We use a 3-tier system: warning, throttling, and termination. At the warning level, we alert the engineer. At throttling, we inject a delay prompt to slow the agent down. At termination, we cut the API key access for that session immediately. Look at this comparison table: manual monitoring vs automated kill switches. The difference isn't just money, it's the survival of your service during a weekend spike. But how do we use this failure data to actually make the agent better for the next run? The final piece of the puzzle is the feedback loop. Don't just let trace data sit in a database. We use trace data to automatically fine-tune our system prompts and control gates. If an agent consistently fails at step 4 of a process, that data is piped back into a reviewer agent that suggests a prompt modification or a new constraint for the orchestrator. This is what we call evolutionary loop engineering. By analyzing why the crash happened, was it a database lock, a logic drift, or a cost overrun, we harden the system gates. We've moved from reactive fixing to proactive system design. This journey through the trenches has taught us that failure isn't just an option, it's the primary data source for optimization. Now that you've seen the war stories, it's time to put these lessons into a structured, actionable format. Let's head into our final chapter, the 2026 Best Practices Checklist, where we summarize everything into a foolproof architectural blueprint. In the field, we see many treating agents like magic black boxes. By 2026, that era is officially over. If you want production reliability, you need to adhere to the engineering manifesto. Rule 1, deterministic output enforcement. You can't just hope the LLM follows the schema. You use libraries like Pydantic v3 or strict JSON schema enforcement at the gateway. Rule 2, every loop must have a maximum entropy cutoff. If the agent hasn't reached a state change in 3 cycles, you kill the process immediately. Rule 3, state is externalized. Never keep the agent's memory only in the context window. Use a persistent state store like Redis. Rule 4, observability is non-negotiable. If you don't have open telemetry traces for every turn in the loop, you are flying blind. Rule 5, prompt versioning. A 1% change in a model's weights can break your logic. Wait until you see how these rules get broken in the most common loop designs in the next scene. Let's talk about the God agent anti-pattern. I see many architects trying to make one agent do everything: planning, execution, and verification. In 2026, we have moved to micro-agent orchestration. On the left of our comparison, the naive loop, it's monolithic, hard to debug, and costs a fortune because every retree reprocesses the entire context. On the right, the modular orchestrator, specialized nodes, short context windows, and clear handoffs. Another failure point is implicit retrieves, where the agent gets stuck in a loop apologizing. Real engineers implement hard gates if the validator fails twice. The loop escalates to a human or a more powerful model like a GPT-5 class system. It is the difference between a system that looks smart in a demo and one that actually stays up at 3 a.m. during a traffic spike. But can we automate the fix for these architectural mistakes? The next shift in 2026 says yes. By late 2026, we are seeing the rise of self-evolving orchestration. It is no longer just about us writing the code. It is about the system monitoring its own failure rates and suggesting prompt optimizations. We started with hard-coded chains in 2023, moved to dynamic DAGs in 2024, and now we are at autonomous feedback loops. Imagine a system where an optimizer agent watches the logs of your production agents. If it detects a 15% failure rate on a specific tool call, it automatically generates a new few-shot prompt, tests it in a sandbox, and submits a PR to your repository. This isn't science fiction. It is the logical conclusion of LLM as a judge combined with modern CI/CD pipelines. The timeline of this evolution shows that the developer's role is shifting from coder to orchestration architect. This evolution is happening faster than we expected, leading to one final set of principles for your architecture. We have covered a lot of ground today, from the gritty reality of loop failures to the high-level architecture of 2026. The key takeaway is simple. Agents are just another engineering component. They require the same rigor as a database migration or a distributed microservice. Reliability doesn't come from the intelligence of the model. It comes from the guardrails of the system. We've defined the manifesto for determinism, identified the anti-patterns that drain your budget, and looked at how self-evolving systems will change our workflows. As a senior engineer, my final advice is to build for failure first. Assume the agent will hallucinate, assume the API will time out, and design your loops to handle that gracefully. Now that you have the checklist, it is time to put these concepts into practice. In the next chapter, we are going to turn these theories into a concrete action plan for your current projects. Don't miss the actionable next steps. Don't just close this video and go back to your old spaghetti code. Within the next 24 hours, I want you to perform a loop audit on your most active agent. Look for any while loops that lack an explicit escape condition or a maximum retree depth. Those are your ticking time bombs. Replace vague system prompts with structured state machine logic using tools like Pydantic AI or updated land graph patterns. Implement a basic self-correction node that checks if the output matches the schema before it ever reaches your user. In the field, we see a majority of agent failures happening because of missing validation steps. By adding a simple reflection gate tonight, you're already ahead of the pack. This isn't just about making it work. It's about making it resilient enough to survive a production environment without you being on call 24/7. But how do we move from these quick fixes to the high-level engineering that will define the rest of 2026? The answer lies in deep research. Mastering agent orchestration in 2026 requires than just knowing how to call an API. You need to dive into the architecture of recursive, self-healing systems. Start by studying recent breakthroughs in agentic reasoning, where models generate their own internal verification steps. Look into the multi-agent supervisor pattern, which is replacing the single-purpose chatbot. In the real world, we are moving away from linear prompt chains and toward dynamic graph-based execution. You should be comfortable with asynchronous state management and persistent memory across long-running loops. This is where the distinction between a hobbyist and a senior engineer is made. If you're not thinking about how your agent recovers from a 404 error during a tool call, you're not building a product, you're building a prototype. Understanding these advanced frameworks is your ticket to leading high-scale AI projects. But wait, even the best tech fails without a proper human-centric safety net, so let's address the human factor. The biggest question I get from engineers isn't about code, it's about trust. How do we let an agent autonomously delete a database entry or spend real company money? The answer lies in escalation paths. In 2026, your design must include a human-on-the-loop interface where the agent can pause and ask for permission when a high-risk threshold is met. Don't build black boxes. Build transparent systems that log every decision-making step in a way that humans can audit later. This lecture series was designed to give you the blueprint for exactly that kind of sophisticated orchestration. We've covered everything from loop failures to the best practices of 2026. The transition from a developer to an agent architect isn't overnight, but by applying these patterns, you are protecting your system against the inevitable hallucination storms of the future. You now have the tools to build agents that don't just act, but think and recover. This is the end of our journey together, but for your agents, the real production journey starts today.